So we've studied infinite limits, and now we're going to look at limits at infinity. What's the difference? Well, an infinite limit would be something like, if I want to take the limit of 1 over x squared as x goes to 0, this goes up to infinity from both sides, right or left. So that's what we call an infinite limit. You're evaluating the limit. It doesn't exist. We could say does not exist because it doesn't. But if we can be a little more specific with why it doesn't exist. It's unbounded. Okay, so a limit at infinity is a little different. So a limit at infinity is I'm going to go to infinity and I'm going to see what happens. Does the function go to infinity? Or is it bounded? Like in this example, as this weird function looks like some kind of trig function oscillating, but as x goes to infinity, it goes to a line, or it goes to a constant value, L. Right? So the limit exists. Right? It's in calculus great. We have these concepts where x is going off to infinity, but the limit actually exists. Let's look at an example. So if I wanted to find the limit as x goes to infinity, we can do positive infinity and negative infinity. We'll look at both of those. Of this function, what do you think's happening here? If you had to guess, I mean, that's hard to do, right? You're saying, well, wait a minute. I got 40x to 4. That's a really big function. I mean, as x goes to infinity, that thing is going to infinity. All right, that's blowing up. As x goes to infinity, the denominator is going to infinity. That thing's blowing up. So how could that possibly have a value? Well, if you think about it, at infinity, that doesn't matter, right? If you have a number that's going super big, trillion, 10 trillion, take one away, that's not going to matter. Expand that a little bit, and this is where it gets a little more complicated. That doesn't matter either, right? This guy wins so much that the x squared doesn't matter. X to the 4th blows up so much bigger at infinity that x squared doesn't matter. Okay, so kind of an intuitive thing would be, well, at infinity, nothing really matters for like a rational function except for the highest terms. So this would also be equivalent. I can do this or more analytically here in a second as well. But this is kind of the intuitive way to do this problem and the easy way. And I get 4. Think about that. As x is unbounded, this thing's going to 4. Can I do this in a more kind of analytical way? Can I do some algebra to support that? Well, let's see. I could say there's a lot of algebra in calculus, right? So you might say, well, wait a minute, I could investigate this guy a little further. Why not divide or multiply by a form of 1? And in the form of 1, I get to pick, and it's going to be this, and I'll show you why. Right, I'm going to multiply this whole thing by 1 over x to the 4th divided by itself. All right, and then that means I divide each term, or multiply each term by 1 over x to the 4th, and in essence dividing by x to the 4th. And I get this, the limit as x goes to infinity of 40x to the 4th divided by x to the 4th. Plus 4x squared divided by x to the 4th minus 1 divided by x to the 4th. Same thing in the bottom. 10x to the 4th divided by x to the 4th plus 8x squared divided by x to the 4th plus 1 over x to the 4th. Okay? Right? I'm allowed to do that because I'm not worried about, I can't divide by 0, right? That'd be a problem. But I'm not worried about x being 0 because x is going to infinity. So we're just worried about big values of x. So, what did we learn about limits from before? Oh wait, we didn't learn this. What can we ascertain from this in particular guy as x goes to infinity? Well, that's going to 0. And this will be a big part of limits at infinity, finding ones that are 0. Right? 1 divided by something that's ever increasing is getting ever smaller. Right, so 1 divided by 1,000, really small. 1 divided by a million, really small. So that's going to 0. That goes to 0. Same thing here. That goes to 0. It doesn't matter if it's plus or minus. And even these guys are going to 0. right? Which is a more analytical way to say what I said before. That doesn't matter, right? 4x squared over x to the fourth would reduce to 4 over x squared. And as x goes to infinity, he's gone. Same thing down here. The 8 and the 4, they don't matter. So they all just go to 0. And then I'm just left with these leading two terms. And this is why I divided by x to the fourth, because that makes the most sense. I can find my guys that are going to 0. And then this just leaves me with 40 over 10, which is, all right, let me be a little bit better with my notation, because I want you guys to be good with your notation. This limit as x goes to infinity is equal to this limit as x goes to infinity, which is a constant, and that's 4. And that's it. And that's going to be one of our techniques. All right, we'll have a lot of rational functions here. All right, and we're going to look at the graphs of these to support what we're doing here in a minute. Let's see if we can do a couple more. Let's see. Let's knock out the easy one. This one. See if you can figure it out. Tell me what the limit is as x goes to infinity. And then we better look at negative infinity as well. See if you can get it. So as x goes to infinity, 2 goes to 2, right? That's always just going to be a constant. You can use your limit properties here if you want. This is what I'm asking you to do, is find the limit as x goes to infinity of that thing. So that's equivalent to the limit of the 2 plus the limit of 10 over x squared as x goes to infinity. So as x goes to infinity, what's a constant do? Nothing. Stays at 2. As x goes to infinity, what's 10 over x squared go? 0. Easy. What about the other way? Let's try and be good about our notation. I'll say, all right, let's find the limit of f of x as x goes to negative infinity. That should be equivalent to the limit, and then I can apply my property of 2 as x goes to negative infinity, plus the limit 10 over x squared as x goes to negative infinity. All right, well, and that's, these are equal, these two are equal, and that's going to be equal to, where does 2 go as x goes to negative infinity? Nowhere. Stays at 2, right? It's constant. It's always 2. Where does this thing go as x goes to negative infinity? Does that make a difference when it was going to positive infinity? Well, sometimes it does. In this case, it does not. Right? If I plug in, another way to think about this is how we first looked at limits. You can plug in values. Plug in negative 1,000,000, negative 2,000,000 in your head. This becomes positive. Right? So in fact, this limit is actually the same as this limit. They're both going to 0 from the same side. Okay. How about this one? Let's do this one's a little tricky, so we're going to, this one will be different, and I'll try and explain why these will not be the same for this problem. So we got to watch about these roots. You'll see some of those. This one's easy. I say this all the time. A lot of calculus is just knowing your algebra. So if you can, what I do with this one, I just picture this function in my head. In algebra class, we called it end behavior. What's the end behavior of this thing? As x goes to infinity, and if you need to think about it, just plug in values that are getting bigger and bigger. What happens? It goes to infinity. So we can have an infinite limit for a limit at infinity. Right? That is, as x goes to infinity, our functions can also blow up. Or as x goes to infinity, we can have a limit that exists. All right, and what happens on the other end? Well, if you just, or you can just picture the graph. We'll look at graphs because they're very, very helpful. But I want you to be able to think these out and analyze them without just looking at the graph. That's x cubed, so as x goes back, y goes down. All right, how about this guy? Well, this one's a little tricky, so I want the limit as x goes to infinity, a limit at infinity of this thing. And I can approach it the same way. This doesn't really matter at infinity. Or we could divide like I did here, but I don't, or like I did where? Like I did here. I'm okay with you guys saying, well, for these rational or rational type functions, these ones don't really matter. I think that's that's intuitive enough or straightforward enough that we can focus on the larger ones. All right, this is the textbook method. And if you want to do that, that's great. That's a really analytical approach. But I think we're okay with understanding that the lower powers don't matter. All right, and that's going to hold for this as well. So you might guess what happens here. All right, that would be equivalent to the limit as x goes to infinity of f of x. Okay, so what happens with this? Well, the square root of x, that's tricky, right? Square root of x could be plus or minus x. So just think about it. You know what you're plugging in. You're plugging in positive values. So this is positive and this is positive. And so the square root of like 1,000,000 squared is 1,000,000. And this would be 1,000,000. So that's 1. Can you do an extra step? Well, if you can come up with 1, you come up with 1. That's it. Does that make sense? Because, again, you can think about one way to do this is just what's happening as x goes to infinity. 1,000,000 squared square root is 1,000,000. And then this would be 1,000,000. 1,000,000 over 1,000,001. Right? Or, algebraically, if everything's positive, then the square root of x squared is positive. And that's going to be positive. You can think of those as positive, and then it's 1. But what about over here? This one's different. Right, as you go to negative infinity, your numerator would be a negative. Think about negative 1,000,000. And then what happens down here, this is negative 1,000,000 squared, positive 1,000,000 squared, square root positive. In other words, this is always going to be positive. And this is going to be dependent on that sign right there. So that would give you a -1. Those ones are a little, you got to think about those a little more. Okay? So that's it. There's some kind of analytical approach, but it's also just kind of knowing your algebra and then just kind of reasoning it out what's happening. All right? If I gave you the graph, then it's a lot easier. Right? Here's the graphical approach. This is what the function looks like. We did this without knowing what it looks like graphically. Right? So if I gave you the graph of this, then it's real easy. Right? Because I can see as x goes to infinity, this is an asymptote. And these functions you're not as familiar with, so you might not know it. With rational functions, we'll talk more about here in a minute. We're a lot more familiar with those when we can talk about both vertical. We've already talked about vertical asymptotes. We can talk about these horizontal asymptotes. So this is the limit, which is the same, right? The horizontal asymptote y equals -1, but it's also the same as the limit of this function as x goes to negative infinity, right? As we go back this way, is equal to -1. They're the same. All right, so that's our relationship there between a limit at infinity that exists is going to be equivalent to the horizontal asymptote.